Today we're doing a live video demonstration of Smalltalk, a system running on the Xerox Alto. So Dan, could you maybe tell us what exactly was Smalltalk?
Okay, well there have been a whole bunch of different Smalltalk implementations. The first was called Smalltalk 72, and it was used for educational purposes. It began with some ideas that Alan Kay had, and he worked together with L. Goldberg, and we actually organized a number of classes at Xerox PARC to see what it would be like for kids to use this kind of a programming environment. And a lot of the principles came from some of the work of Seymour Papert. But the specific language we had was, the idea was to do everything as sending messages, which was a revolutionary idea in those days. And the Smalltalk 72 system was a very simple token interpreter. And maybe we'll talk about that some other time. But essentially, the programs that were written all ran as separate tokens, and whenever a token was identified, it got looked up, and then the subsequent actions depended on what was looked up there. And with that model, it was very flexible, so it allowed people to define their own classes and how objects would respond to messages in a very simple way. And so that's how the early programs were written, how we taught kids. But there were some problems involved with doing things that way. Which is that it ran very, very slowly. These programs were programs that were parsing themselves as they ran, which made them run, 20 times slower than competing systems. And another problem, which was the real Achilles heel, was that you couldn't actually tell what a program meant without sort of running it yourself, because you'd see a token and you didn't know how the rest of the sentence, as it were, parsed without going and reading what the computer would have done. And that wasn't so bad, because for the most part people wrote programs that made sense. But if you want to compile a program and make it run fast, the meaning has to be all unambiguous from the get-go. And so Smalltalk 72 was not compilable, and so could never run really fast. And that's some of the background for our talk today, which is about Smalltalk 76, which was the first sort of modern Smalltalk where the same kind of message patterns could be expressed in the program, but they could actually be compiled. They were unambiguous. So maybe that's one place to start, is the syntax of Smalltalk 76 was unusual for programs at the time, but basically there were three kinds of messages: unary messages like string length, and binary messages, the kind of things you expect like arithmetic, A times B. Those are all the messages expressed with non-alphanumeric characters. And then keyword messages. And these are things like, set X and Y. So you've got two parameters there. And in Smalltalk 76, the keywords have colons at the end of them. And so this allowed multiple parameter calls to be expressed without needing a lot of parentheses. So that made it also nice. Another thing I'll say, just sort of in the run-up to the work on Smalltalk 76, was that in the context of this, these programs were all running on the Alto. And the Alto was an amazing machine for its time, but it actually was very small. So it had 64 16K 16-bit words of memory, or 128K in current parlance. And half of that space was used up for the bitmap display. So that made it an even smaller machine of 64K. And then to interpret the Smalltalk language, it took about 32K of code. And so now we're down to about 30K of space for the entire user's program and the Smalltalk system that sort of supported it. So there was an intermediate generation of Smalltalk that never saw much use, which was called Smalltalk 74. And it was very much like the Smalltalk 72 language, except that we built a virtual memory for it. And that memory was called OOZ, and it's written about in the Byte magazine. And the important thing about it was that it it split up object pointers into essentially two parts. One was sort of like the class of an object, and the other was an index of how many. So we allowed 512 classes and 128 instances of each of those. And for things that you made lots and lots of, like points or rectangles, there might be several, so we call them pseudo classes, that all were the same class, but they allowed you to have more than 128. And then, of course, you've got also the problem of variable length objects, and we split those into octave sizes. So that's how that was handled. This meant that at least in terms of addressing, we could talk about something like 60,000 objects in the Alto. There was a small range used for integers, just to be efficient. That then gave us a much larger address space than the physical Alto supported. So what we had to do was to we could address the disk that covered. The disks we used were about 1.5 megabytes or 2 megabytes. So it allowed us to write programs that large, but they had to be paged and organized into memory. To do that with a conventional paging memory, we would never have been able to do it in such a small space. But by using a hashed object table, so we would take that object pointer, look in a hash table, and figure out the associated location in memory of that particular object. We could very compactly represent the working set. And you'll see that when we're running, sometimes it may shake a little bit and take a little while to get its working set established, but then it ran very efficiently at that point. So the Smalltalk 76 is built on that, and the system itself is something like 150K, and we built applications that were over 1 megabyte, all that ran in this tiny sort of 30K of actual working space on the Alto. I want to talk a little bit about the sort of the semantics of Smalltalk 72. Smalltalk 72 was very simple, but and it had classes and objects, classes and instances in its semantic model. But the way that classes were done, classes themselves were not first-class objects. So the meta system wasn't as clean as it might be or as powerful. And also the stack frames accumulated when one object called another, those also were not first-class objects. And we learned a bit about that when we were doing Smalltalk 74. And when we finally did Smalltalk 76, we made sure that all of those sort of meta objects in the system were first-class objects. And we'll see some of that in the examples here. Let's see, I'm not sure, do you want to ask another thing or two?
Yeah, could you talk a little bit about your particular role on the project?
Okay, sure.
And how you got to be on the project.
Yep, okay. Okay. So I originally came to Xerox PARC working with George White on speech recognition. And my office was across the hall from that of Alan Kay. And while I was interested in the work that I was doing with George White, I kept being very much interested in the conversations that I heard Alan having across the way. So finally I walked across the hallway and said, "Hey, what are you doing?" And he talked to me about his interest in doing a new language that would be easy for kids to use. And we got started on it. And I think Ted Kaler was also around at that time, and Alan had this plan for how to build a language in which all computation was done by sending messages, which could be a much more general way of doing things and has lots of good properties associated with it. If you build a system that way, it can be much more modular, as we know now. You know, it's the world of object-oriented programming, essentially. And I was fascinated by this and just took to it. And when Alan sort of laid out the sketch of an interpreter for such a language, I took it on as my responsibility to actually build one. And the first one I built was in BASIC, of all things. It was because I was having a child at home and wanted something that I could run at home, and there was BASIC time sharing available at home. So the first Smalltalk interpreter actually ran in BASIC. But we got that allowed us to sort of debug the whole scheme. And then at that time, the Alto was being built at Xerox PARC. And it was built to run the same code set as the Data General Nova mini computers. And so I got control of one of those and started porting the work that I had done into that and got Smalltalk running in sort of emulation mode. That was the beginning of Smalltalk 72 on the Data General Nova. And then when the first Altos were available, we right away moved it over and had that running on the Altos. And the project evolved then. As I said, we did a number of classes with kids trying out Smalltalk 72. And then, you know, we were software geeks. We wanted to do more and more. And it seemed like this was actually a powerful system for doing things, except it was too small and it was too slow and it didn't have a good meta system. So we worked away at those things. And there came a time I was wrestling with this notion of how can we have something that's got as nice a message sending syntax as Smalltalk 72, but that's compilable. And I still remember there was a weekend I spent at Pajaro Dunes. I think it was my birthday. And I came up with this way of doing a keyword syntax that would have that same feel, but would be rigorously compilable. And together with that came, similarly, a design for an engine that could execute code compiled from that. And I don't know if this would be a good time to talk about that diagram. So I'd like to explain how the syntax of Smalltalk 76 can be compiled into a compact structure as the architecture of the whole virtual machine, and then the dynamic structures needed to evaluate. So what we're looking at here is a method in class rectangle, which is the method that tests is a point within that rectangle. And here's the source code for it. It contains a point, and the code says return the origin, return the fact that the origin is less than the point given, and the point is less than the corner. And this less than operation is a graphical less than. It means is to the above and to the left. So this is the Smalltalk code that's being compiled, and so it is in a message dictionary in class rectangle. So here's the class object. Its title is rectangle. And its part names, these are the instance variables, are corner and origin. And it's got a pointer to its superclass, which is, in this case, is class object, from which it inherits other methods. And it has a pointer to the message dictionary, and this is the dictionary that contains all of what's needed for the methods in the class. So in this case, the name is contains with a colon. The source code is what I just described. Contains point is the origin less than point, and point is less than corner. And the compiled method now is a pointer down to this object. And it's a compiled method. And it has setup information in a header, which has stuff like the number of arguments and things like that, and also pointers to literals if there are any. And then the actual byte codes for the virtual machine to execute. These are like the instructions. And here it says corner, point, less than, point, origin, less than, and return. And just to say that, corner in this particular case will be an instruction that is like, you can see that corner is the first instance variable. So this will be an instruction, it'll be 8 bits, and what it means is push onto the stack the first instance variable. And this means push onto the stack the argument. And this means send the message less than. Okay, so it's not a procedure call, it's a message send. And so on. And then here do the same thing with this part. And then this AND operation is an operation between Booleans. And this last operation is a return. So this operation here, this AND, will have left a true or false on the stack, and this will return it as the value. Okay? So that's how all of this works. And the dynamic structures then, to make this happen, there's when this method gets called, it creates this object here, which is, we call it a context. It's a real Smalltalk object that is essentially a stack frame as we know them conventionally. And it has a pointer to the sender and a pointer to the current method. Obviously it needs that. It's got a PC, a program counter, which is the pointer into the current byte codes. And then it has a temp frame, and this is the place where the argument point will have been pushed. And then it's got also the stack, which is it's the computation stack. And here it's got a stack pointer that records the current position. And it's got a class for the pointer for the method class, and that's needed for if you're running an inherited method. There will be a pointer to the class in which that method is found, but it also needs to know the class that this one actually was in. And then it's got a pointer to the current receiver, which is self. And here is the actual rectangle with its origin and its corner, and those point in turn to points. So that's the whole architecture of Smalltalk 76. It's very simple, and because of being simple, it was possible to actually get most of this kernel operation to fit in microcode so that things would perform decently on the Alto, which was not a fast machine. Less than a MIP in many sense. So the tradition of all the Smalltalk systems had been that they are basically live coding. So all the time that you're working there, the system is live and changeable. You can, of course, change your programs, but you can also change the system itself. And everything that's sort of a part of the system running is accessible to change. So here's some text on the Alto screen. It's divided up into windows. This was a novel concept at the time. We're all used to that now. And wherever there is text, you can make selections, and you can bring up a menu and ask to do it. That means to evaluate it and print the result. You'll notice that the screen momentarily goes black. That's because it doesn't have to be done that way, but we did it that way because the Alto ran somewhat faster, about twice as fast when it was not displaying. And that's because the Alto was this incredibly simple architecture in which actually putting the bits on the screen was a program that ran. And so it competed with the rest of the processor. So we've just evaluated 3 plus 4 and gotten 7. That tests a huge amount of the system actually because it runs the whole compiler. So that was the first thing that we always ran. And then we would run this one here, which is, let's see, this divide 355 as a floating point number by 113. And the result comes out very, very close to pi. And that was a way that we knew all the floating point system ran. And at that point, it had tested about 90% of the system. I guess the one other sort of significant piece of system code in here was large integers. So in order to run compactly, Smalltalk 76 just allowed for 4,000 small integers. And then to do larger integers, it made them up piece by piece from small integers. So I'm going to print here 20 factorial, which is a large number. So there you can see the result. So one of the things that's nice about this is that although Smalltalk used small integers, we made sure that you could make large numbers with them, because one of the first things that kids want to do who are working with numbers is make bigger ones and bigger ones and bigger ones. So you can make them as big as you want in Smalltalk. So that's just sort of the simple things about getting started with using the system. Wherever there's text, you can select it and evaluate it and print the result. The system itself, it has this somewhat more sophisticated programming interface. This is a Smalltalk code browser, and it takes all of the parts of the system and breaks them down according to classes and the messages for each of those, for instances of each of those classes. And there are a number of categories here, including kernel classes, things like classes, object. So I should say, one of the things that we did in Smalltalk 76 that we had not done in the earlier Smalltalks was to support inheritance. This meant that you could have a class object and put methods in there that all objects would want to be able to support. For instance, how to print yourself. So you find code for that in class object. And here's the code for classes, and code also for contexts. Contexts are essentially the same as we know now as stack frames for a debugger. Those were actually first class objects in Smalltalk 76, which meant that you could write the debugger in regular Smalltalk code. It didn't have to be in assembly code or anything special. And that's the kind of thing that made it easy to do these kind of browsers. Let me take a simple example of some code. Let's look at numbers. And look at something, what's a good example here? Arithmetic. So just to see what code looks like in Smalltalk, here's a method called max. So if you want the maximum of 2 integers, you would say a max b, and A would be receiving the message max with the argument B. And the way to understand this code, it says, am I myself less than the argument? If so, return the argument. And then there's an implicit, if not, return myself. So that's how that code works. What's notable about this is that this is in class number, and all these other kinds of numbers, floating point numbers, integers, large integers, and so on, fractions if you define them, they all inherit this same method. This allowed the system to be much smaller than a lot of other systems. If you have a message-oriented system, then you can have that kind of inheritance, because when this makes the test, am I myself less than the argument? This less than operation it's not a procedure call, it's a message send. And so that message send would be meaningful for fractions, for floating point numbers, for integers. And therefore, this exact same code can be inherited by those other classes. So that can make the system, 5 times more compact in those kind of cases. We can also take a look at how we manage to compile this message send into actual byte codes. Let me let me do this. I'm going to print out, what I'm selecting now says it's going to class number, looking for the method whose name is max, and printing it as bytes. So there are the actual byte codes for this method, and those include a couple of bytes of header information and about 10 bytes that correspond to these tokens. So the first one says, push a pointer to myself on the stack, and then it'll say push a pointer to the argument on the stack, and then send the message less than, and so on. And the way you would find out what these numbers actually are and how the thing works is you actually can go and look and see how the system works. So we'll take a look. In kernel classes, we'll look at context. And here are a bunch of the operations that the virtual machine can do. And let me go down here to this message called step. So when you have a situation where a computation is in progress, each cycle of the virtual machine involves taking the next step. So it goes to look for the next byte code, which is the next instruction. It looks at the method it's currently running, advances the program counter, PC +1, and then looks at that place to get the byte code out. And then it tests the byte code. And in this particular case, it says, is it less than octal 200? Then it's a load instruction. And so on. It goes through all the different ranges. And these are the things that it will do. For instance, push a field of the instance onto the stack, push a temporary onto the stack, and so on. So this method here is actually a complete simulation of the Smalltalk virtual machine, which means that the debugger is capable of single-stepping a program. And the interesting thing about this is that this is actually the first part of Smalltalk 76 that was ever written. And it was actually written in the earlier version of Smalltalk called Smalltalk 74. And I don't have that version to show you, but when we were beginning to build the system, we were able to put together little pieces of code and get more and more of it running in that way in the earlier host system. And then we wrote the compiler that would compile this new language and got it to run. And then eventually we wrote the machine code and microcode to make this all run live. So I'll come back to you and sort of see what the next thing you're curious about here. So in addition to just these kind of simple arithmetic things that you could try out very easily, just because the system's live, like this little division that happens to produce a result that's very close to pi. You could also do things that would do graphical effects on the screen. So here's an expression that sends the message new to class rectangle to create a new rectangle, then sends the message from user to that rectangle, which will ask me to indicate coordinates on the screen, and then it sends this message comp, which will reverse the bits on the screen exactly where I was. So I'll select that and do it. And do this. And so you can see it has reversed all the white and black there. So being able to play around like this and just do stuff, whatever you think of doing, is really nice for invention because you play. And so one of the things that we wound up doing sort of by accident is creating another rectangle that's kind of offset by this one and doing the same thing. And what you see is that it actually, this is a cheap way of putting a border around an area, which is to complement it once and then translate it and complement it again. So the idea occurred to us to actually try that out. One of the things that we got back from some users of this system and others at PARC was that to non-computer users, it was scary to have this big black hole appear in the screen when you do a big selection. So one of the things we wanted to try out was, supposing we didn't do that, but supposing we just drew a border around it. So from what we learned here, we thought, maybe we could just change the way that selection worked and throughout the system and see how that felt. So one of the things you can do in this Smalltalk system is you can interrupt it in the process of doing a selection. And you get this, you get a debugger come up on the screen, and you can then, this just says that you stopped me in the middle of doing something in the paragraph editor, which is useful, for instance, if there was a problem. But we can find out much more by reframing that and getting a sort of a fully capable debugger. And this uses the fact that stack frames and contexts, all of that in Smalltalk 76, they all were actual objects. So it was very easy to write a debugger that could go look at a suspended process in that manner. So I've asked it to give me the full stack. And here it's giving everything from out at the, it's sort of at the user scheduler. It's in a paned window, which was a browse window, and it was in a code pane doing an each time loop. And then there it was checking for the mouse button being down while it was doing selection. So let's take a look at that. So in this, you can actually look at the source code that was operating at the time. And here's some complicated code about how it's, checking all of that. And let's see what that was calling. that was calling this routine called select a point, and it's going through and finding where the character is. And now it calls this routine, which is complement from hair 1 to hair 2. It talks about hair being the sort of the hairline between characters when you're selecting. And here's actually a comment about this, exactly what we were talking about, which is the sort of the first partial selection on a line, and then the complete lines in the middle, and then there's a partial selection on the last line. And you see there, it goes through this code. It's a little bit hard to see because I've got a small window on it, but it's telling itself to do comprect on these various areas. See the comprect, the first partial line, here's the block in the middle, and the last block. So if we could change the comprect routine, that would be useful and might tell us what we want. So let me get another browser here.
And what object is being sent these messages?
So in this case, it's a paragraph editor.
Paragraph editor.
Yeah. Did we figure that out last time?
Yeah, which is a subclass of text image.
Yeah. Yeah. So let's go find that. But I think we found that code in text image, didn't we?
Oh, actually, it's in the form path
Yes.
image category.
Yeah. There we go. Yeah, there's text image. And we'll look in selection. Yeah, so here's the routine comprect that's being called at all the places in doing selection. Let me do this. We've got a complete blank there. How can that be? Let me see if I have no understanding about this. Just a second. It's very strange.
Are the changes that we made not there?
Yeah, it appears that it's not findable. We'll see what it's doing.
Okay.
So I just decompiled it.
Oh.
And let me see if that has helped bring it to life at all. For some reason, the source code didn't get preserved. So we find comprect, and this is a routine for which there happens to be no source code. That may be, but
hopefully the changes we made.
But don't despair. Let's just try this. Smalltalk 76 can decompile its code. So here you can see what it's doing is it's taking the incoming rectangle, and let's pretty it up a little. Rect. And tell it to do that again and again. It's making a temporary rectangle, which is the incoming rectangle intersected with the frame and the window. And then it's telling it to comp, which will turn it black and white. And what we'd like to do is to take this, let's do let's make a copy of that. there. And in addition to doing that rectangle, let's do T2 copy and translate it by 1 and is it that character? Yeah, what do you know? That makes a point. And yeah, so I've got it there. So this will take the that same rectangle, copy it and translate it, offset it by 1 pixel in each direction, and then complement that. Okay. So let's compile that.
And the last time we did this, we accidentally used the wrong character.
Yeah. So when you're doing work on the system that you're actually using, you have to either be very careful or be ready to bail out in a hurry. Now, see, right away I've changed that part of the system, and it's now actually working. And we can go back to the place that we were looking at. Well, we can actually go back let's go back to the debugger. You can actually proceed from that point in the debugger. And it will be finishing the selection that it was doing here. Sorry, I got the wrong browser there. This is the one that we were originally looking at the big selection in. And you can see it's that way. So that's nice. And we could actually, now when we look at that, it's, yes, it's better that it's not a big black area, but it's kind of faint. So it's a little bit hard to see the selection. So we could, having made that change, we might want to just make it go by 2 pixels. And compile that. So what's nice here is, we're in the system running. It's easy to make changes just on the fly. So there's no need to, redo the whole system. So there's the selection now looking like a reasonable piece of user interface to try this out. So, okay. We can find the scroll by.
Do you want to do that in 2 steps? So first enable the live scrolling, and then make the floating point change in a separate step.
Yeah,
so
let me just.
Show.
Yeah, let's go back to some reasonably. That was not simple. Let's see if we can. So that was in scroll bar, right?
I had it written down.
And it's in. Scroll bar each time. Slide it was in.
Yeah.
Okay, and what did we have to change? Oh, we had our cheat sheet beside us at the time, right?
Yeah.
Oh, yeah. What do you know? Okay. We took the trouble to comment that. Good job. Okay. So the system as we used it on the Altos was not super fast, and you've noticed that already. The actual time it takes to move text around is significant. And so we did not try to do live updating. So this would take you to a certain part in the text, but we didn't display it until you let go of the mouse. This made it a little bit faster for us to work with a slow computer. As the computers got faster, we could actually track that. And so by the time that I gave the demo to Steve Jobs, we were running on a faster machine, and it tracked well. And I can show you. So this code was at that time doing live updating, and I'll compile it that way.
So that was on a Dorado?
Yeah. Okay. So now when I drag this down, you can see it's a little bit it's very slow to follow, but at least it does follow. And when Steve saw that, he saw this happening quickly, but in this jerky line-by-line manner. And he said, can't you make that just scroll smoothly? And it took me a while to find the part of the system to change, and I actually did that while they went away to lunch. And but when they came back, I had a simple change for it. And let's go to, I believe that's in, I've forgotten again whether it's in paragraph
It's
editor.
paragraph public messages, scroll up.
Yeah. So all of these routines came through the scroll up method. And here it would scroll by the number of lines, or by the amount of pixels divided by the line height. But because these were fixed, this was an integer, then it simply did an integer result, which truncated to the nearest line. But it was easy to change once we had the tracking. By changing that to a floating point number, and I'll make sure that that's what that says. Yeah, compile. Let me find a big method. Something. Well, let's see. Okay. So now as I drag this, you can see it's doing smooth scrolling. It's jerky because it's slow, but when Steve saw this, it was just totally smooth. So that was effective, and I think I've showed that to you in a faster version of this system.
So could you start by giving us a little bit of context of this version of Smalltalk that you're going to show us?
Okay. Yeah. This is Smalltalk 78, as we called it. It's essentially a copy of Smalltalk 76 that was ported to the Note Taker, which was a research project at Xerox PARC, where we did a complete Smalltalk interpreter that ran on the 8086 microprocessor. So this is the first microprocessor implementation. A couple of things are different about it, but mostly it's all the same code. The major change that was made in order to do this was that we had a pile of Alto Nova code that was the virtual machine for Smalltalk that had to be ported to the 8086. And and lots of it was involved in doing character display, in doing scrolling operations, and all sorts of other bit manipulation operations that could all be done with BitBLT, by that time we had developed the BitBLT primitive. So we implemented that on the 8086, and it allowed us to go from an interpreter size of about 32K down to about 16K, leaving most of the hard work to be done by the little BitBLT kernel, which we did port to the 8086. And that then actually became the basis for the future versions of Smalltalk. But what I'm going to show you here is a resurrection of the Smalltalk 78 interpreter in JavaScript, running in the Lively kernel. And one of the things that's notable about it is that it's extraordinarily faster than the original was. So you've seen the time it takes to move from one browser window to another in regular Smalltalk 76 on the Alto. Here I click, and it's as though the bits are, it's as though the bits were saved, but these are being completely repainted. And scrolling is essentially instant in all these cases, And the other thing is that one of the neat things about having a system which is all done in terms of objects unto themselves is that we did a completely different memory system. So this uses a garbage collected memory system in JavaScript. And the system can actually be much larger than the original one. It doesn't have any of the same limitations. But other than that, it's a faithful implementation of Smalltalk 76, and it's a wonderful one to browse around in just because everything's so responsive.
Okay. And so the next thing that we're going to see is this change that has been famously reported. The work was part of the demos that you guys at PARC did for Apple and Steve Jobs.
Oh, right. Yep.
Could you talk a little bit more about how that demo first came to be?
Sure. Well, yeah, so Steve came with a team to see the Smalltalk system. And what we showed him then was Smalltalk 76, but not running on the Alto, but running on a faster processor. I'm pretty sure it was the Dorado. So it had a lot of this same zippy responsiveness. And during the time that I was giving the demo to Steve, I made the change of how text selection could be changed from block out to outlining, while he was watching. And then he came back saying, couldn't you do it? I noticed that the scrolling goes chunk, 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 chunk by lines. Couldn't you do it in a smooth manner? And that wasn't something that I could simply do while he was watching, but he and Adele and a couple of other people went off to lunch, and I did it while they were away at lunch. So when they came back from lunch, I was able to show it to them. And I'll show you, I can show that in this system because, I've taken the time to, I know where to make the appropriate change. We've got, scrolling is done in a number of places here in the text image class. And what happens is that the scroll bar sends a message called scroll up to the text image. And it's in terms of the number of pixels, and then that gets divided by line height, and it goes to this message scroll by, which is made to scroll by a certain number of lines. But it turns out it's very simple. If I simply convert that incoming number of pixels to a floating point number first, then this division will be in floating point, and so the scroll by message will be, well, let's see, I think I should show you something scrolling just because you haven't seen it in this system without this change. So there it is. It's responsive because it's this is the fast implementation, but it's chunky. So now if we do this as a floating point computation, it will be sending a floating point number there. So I'll say, let me compile that. Something else you'll notice here is that compiling happens in the twinkling of an eye, as it should, of course. And so now if we go back here, you see it's completely smooth. And it's fortuitous that this is the scroll by code, and all of this code simply works just by converting it to floating point. It was written in a nice general way. So things could have worked out that it was not happy with floating point numbers there, but it seems to be. So that's how the change looked to Steve, and he was duly impressed. So I might say a little bit about more about where this implementation went on. Having made the conversion to do all the graphics using BitBLT, the kernel was much smaller, and that then enabled Peter Deutsch to do a new virtual machine for the Dorado at Xerox that used that. And then he also did another implementation for the 68,000, which continued on in that tradition. It also became the basis of the that gave us a fast development environment for doing serious system work, and from that came the whole conversion to Smalltalk 80 and the release of Smalltalk 80 as an ANSI standard software product. And then that continued on for quite a while, and it was essentially that same system that we picked up at Apple again and built the Squeak system using that. And Squeak was the first, and I think it's the only Smalltalk that actually has its own virtual machine written in Smalltalk, which made it really easy to maintain and develop the virtual machine. I think the most impactful aspect of that was that when we put it out in, I think, 1996, we put it out as a package for the Macintosh. But it had all of its source code with it and all of its ability to simulate its own virtual machine. And I think it was within 1 week, Ian Pumarda had ported it to Unix. And then a week or two later, Andreas Raab had done it for Windows. So this ability to have a system that's self-describing and self-supporting makes it incredibly portable. And we also had done a lot of work there to make it was a bitmap display model that was all self-defined. So it didn't matter whether it was on Unix or the Macs or Windows, everything ran bit identically. And we continue to do other work on Squeak, which you'll know about, but you could be partway through a debugging session on Windows and save that and pick it up somewhere else on a Mac and continue the debugging. It was really nice and portable and compatible.
So talk about BitBLT.
Okay.
First, explain that to the audience.
Yeah. Well, so I think I mentioned that the early Smalltalk virtual machines used a lot of code to support character display and line drawing and text scrolling and all of that. And all of those could be done with a single primitive, and we called it BitBLT. And on the Alto, we wrote that in microcode. And then we've written it, that's been an important part of the graphics kernel of all the Smalltalk systems since then. And what's nice about it is that all of the graphics as implemented are actually, you can work on them. They're just like other user programs. You can change them and edit them and see how they work. So here's, in this example of, in this version of Smalltalk that ran on the note taker, we've got here a turtle this is a turtle geometry spiral. And you can see the code says, create a new turtle in this frame, set its color and its width and its inking, and then for I to 100, tell it to go this distance and turn 89 degrees. So what this go primitive will draw a line. How does that happen? Well, let's look at the code for go. And it says go to the current direction as radians plus the current location. So that will make it go in a certain direction. And this uses the go to method, and that's here. And what does that do? Well, it sets its location, puts the pen down, and then does draw from old location to new location. So let's look at draw from. And in earlier Smalltalks, this would have been a primitive with a lot of assembly code for it. But here, it's actually more user editable code that tests for the pen, what kind of a pen it is, and then sets up a bunch of increments. And here is the actual Breshenhem line drawing algorithm, all in editable source code. I'm not going to go and make a change in it, but we can see it at work by running this little example. Okay, so you can see that you get really usable line drawing speed, all in user editable code, and without needing a lot of assembly code for that. I mean, this is probably just a couple of 100 bytes of Smalltalk code.
Could you talk a little bit about how important the ability to code in microcode was for BitBLT and other aspects of Smalltalk?
Sure.
On the Alto.
Yep. So the ability to write microcode on the Alto really made it a much more powerful machine than other similar machines of the time. The microcode actually ran at 5 times the speed of the memory cycle. So where a regular machine instruction in Nova code might have taken a microsecond or 2 microseconds, the Alto actually ran micro instructions at 200 nanoseconds, which made it, for that time, a very fast machine. And it's interesting, the effect it had, this was an extremely scarce resource. So most of just the basic system of the Alto used up most of the available microcode. So there were only about 100 instructions available to do other work in. So as a programmer, you were strongly motivated to find some small key piece of code that you could fit into microcode, and then that part of your system would run 5 times faster, essentially. So with the early Smalltalk, with the Smalltalk 76 virtual machine, that was the first one where we used microcode. This allowed us to put the kernel part of the bytecode interpreter into there. So the part that would step the program counter, pick up the next bytecode instruction, and look it up in the method table for the appropriate class. That happened in microcode, and that allowed Smalltalk 76 to be a performant and usable system for that time. It actually allowed us to develop the source code browsers that really shifted the whole way of people doing integrated development environments in the industry. And then the next step we did was to this change in the graphics model by implementing BitBLT in microcode. It allowed us to do character display, line drawing, and text scrolling operations. And what we could do with characters was much more flexible than what had been there in the Alto. We could do synthetic, bold, italic, and actually stylized fonts that you see, and all the kinds of handy things in the graphics interface. It was responsible for the birth of pop-up menus because it was easy to take a rectangle of the screen and save it somewhere and put another image there and then pop it back up.
Oh, right. There's a story of you doing a demo of that at a dealer.
Oh yeah.
And somebody said, "Did I just see what did I think I just saw?" Can you tell that story really quick?
Sure. Yeah. So this was we gave there were these weekly meetings called Dealer that were held by the computer science lab, which was sort of a competing lab to ours there, and we always attended because we really liked the people in that lab. And we were the sort of Smalltalk crazies, but often it turned out that somebody would have an idea and we'd go back and get it running in an hour, and Smalltalk maybe not as fast, but we tried out a lot of things, and it was a nice creative back and forth. Anyway, we had gotten I had gotten BitBLT working in Smalltalk 74, and we presented it at one of these dealer meetings, and one of the things I showed was a pop-up menu, and it's funny when I brought up the menu and did, I think it was one of these things where I said do it to execute something. Peter Deutsch turned around and he said, "Wait a minute, did you just do what I think you did?" And yeah, and so that was the first time that we showed pop-up menus, and it was also a great example of technology transfer, because I think it was the very next day, Smokey Wallace from the product division showed up in my office and said, "I just heard about BitBLT and I want to know all about it." And he then went on to be the person to do that work for one of the Xerox product machines.
The Star or a different one?
It was a precursor. Yeah. Yep.
One of the D machines.
Yeah.
Okay.
Yep. All right. Well, I thought one of the things we could look at here is some of the work that was done with turtle geometry. This goes on from Seymour Pappert's work, which we did in Smalltalk 72, but we preserved that functionality in Smalltalk 76. And we've got a few examples of that here. And a lot of these just draw scratches on the screen. So here's because we were just doing experiments, and we would clear the screen when we wanted to do a pretty version of this. But this basically says, create a turtle, initialize it, and then do a drag and curve of order 8. Well, actually, I'll tell it to erase first so that the screen is white, so you can see it.
Is his audio okay?
Let me, that was a good time to not do that. Okay, so let me just say this is creating a new turtle, initializing it, erasing the screen, and then doing a drag and curve of order 8. And the drag and curve is a fun shape. It's got a really simple recursive definition. You can see it here. Let me refresh that now. It's essentially the shape you get if you take a piece of paper and let's see. If you fold it to a right angle and then you fold that to a right angle, you can see that's now a drag and curve of order 2. You keep folding and you get that shape. We've got let me cancel that. Here are here are a couple of spirals which are done let me just make sure that we get and this will just draw them on the screen, one of overlapping one way and the other overlapping the other. And all it's doing here is drawing a spiral with not quite a right angle at the corners. You'll see it as it goes. So that's turning 89 degrees on each corner. And it has this nice precession. And then that's drawing another one over it, turning 91 degrees. And let me go here. Here's a mandala being done. This is where you take a circle and do a bunch of points around it. This is with 30 points around it and a diameter of 400. And you connect every point. And you've seen these, it's something that a lot of people like to do at art fairs by putting a bunch of nails and doing different colored threads. We did colored versions of this, so the Alto did not display color, but we did have the ability to write the images onto a printer description file, and then that could be printed on our laser printers. And we did have a couple of colored laser printers, so it made a really pretty picture. But even in black and white, it's kind of nice. So let me go here. I'll clear the screen again. And let's see, we've got the Hilbert's curve. Let me do this. I'm going to do a quick version of this. Hilbert 4. We'll just do 3. A Hilbert curve is essentially where you take a line segment and recursively break it into a sort of a cup shape. See, there's the cup shape, and here are the various ones there. It's another space-filling curve. And these are fun to turn into tiles if you can fill it. We didn't do filling operations on the Alto screen, but you can actually make ceramic tiles out of it and cover your floor with pretty patterns. Okay, that's most of what we have in the turtle, except when Hanson and I were going through this, we found a method that I had completely forgotten about. And that's this one that says, this will show a character string in a font driven by the turtle. So let's see what we've got here. Turtle init with 3, turn 45. Yeah, so we'll try this one out. This will probably just do it on the screen. So it's saying to create a turtle, initialize it with a pen width of 3, turn to 45 degrees, and show the text string hello there. And there it goes. And what it's actually doing, this is a primitive that Ted Kaler wrote, which goes in and finds the font in memory and picks out the bits and then tells the turtle to do a dot. Which seems like a really hard way to do things, but it allowed us to use the angles of the turtle and the scaling of it to make things bigger and at different angles. So we had a lot of fun with that. And let's have the screen clear when we start this. Actually, I want it really clear. Exit to overview. Okay. Here's a simple spiral routine, which just tells the the turtle to repeatedly go a certain distance and turn a certain angle. And this is turning just 89 degrees, a little bit less than a right angle. So instead of doing a square spiral, it does one that precesses. And let me clear the screen before we do this. Turtle init erase. Yeah, I always get that. So it's going to do one spiral, and then it's going to go back to home, back to the center, and do another spiral, rotating the opposite way. You can see it precesses in that direction because of only turning 89 degrees. And then it turns, this second one uses 91 degrees, so it precesses the other way. Then they overlap in this pretty fashion. Okay, I think that covers the turtle geometry stuff that we were working with.
Good.
Dan, may I ask a quick question about the turtle geometry stuff? Is it the case that when, we've talked before about Smalltalk and the motivation for, children to interact with and use the computer as a tool, was the turtle graphics kind of the most prominent example prior to the Smalltalk work for kind of children using computers?
Yeah. So this was a real, I think, a breakthrough that Seymour Papert made, which was to teach kids about geometry from a local frame of reference. And you could explain it to them so easily by saying, they would take a command like go 10, and so they take 10 steps and then turn 90, and they'd turn 90 degrees, so they could see that themselves physically. So then programs built that way made sense to them, and they could sort of anthropomorphize to understand what was happening. And we just did an implementation in Smalltalk, and in the early Smalltalks, the syntax was so simple it was really easy for kids, in a one-line program you could do something really fun, and that got them motivated. Yeah, so that's the something that Smalltalk added to that, in addition to a different, a more object-oriented syntax than Logo had, was that because of our system being object-oriented, it was easy for us to have multiple turtles on the screen at once. But coming back to what you said about, is that the predominant way that kids worked with graphics? In the early history of our Smalltalk, yes, it was. So when they wanted to draw a box, they'd do the turtle routine for doing that. Later on, when we got BitBLT working and could easily work with Bitmap Graphics, then our whole world started changing more to kind of image type processing. Yeah, and I could show you the, I found this thing that's a BitBLT example. The Smalltalk 76 system here doesn't have much about BitBLT because we sort of got it running and stably. People were working on it more in the area of programming and development system kind of work. And the BitBLT work that I did was in the Smalltalk 78 fork, which then came back to become Smalltalk 80. But I think I can show you this. Let's see, what we need to do is to look at. And things were sort of put in, let me find this here. Oh, I see what's happening. Cancel this. The system was just being changed all the time, and various things were being tried out, and things got put in different places, so it may not make sense. This class rectangle should be a graphic primitive, but it's in this category called form path image. And the rectangle class has all sorts of stuff that's convenient just sort of for accessing to its parts. What is its corner? So this would return you the actual point there. What are its corners? Then it creates a vector of 4 and then goes through and reads the various corners into an array and passes that back. The thing that I found, let's see where, I think it's in image maybe. Yeah, this routine rotate. This is an interesting procedure. So we had no way of rotating things in a bitmap, except laboriously you could read across there and write them with a turtle, but that would take forever, or write them pixel by pixel. But this is a recursive scheme that says, well, if you want to rotate a rectangle by 90 degrees, you begin by splitting it into quadrants and moving each quadrant over to the next quadrant. And then you do the same thing for each of those within it, and within it and within it. And if you figure it out, you'll see that it will rotate it. It will rotate the actual bitmap. So this is going to take a piece of the screen from 0 to 128 up there. And you'll see it also creates the masks on the screen because we were just looking for bits that we could use. But you'll see kind of how this works. So these are the masks. You can see it's beginning to move them around. And that's the final mask, and there's the final rotated image. I might be able to do that for a larger picture. Let's do this. That would include more of this, so it would make more sense. Let's do 256. And let me, I'm going to clear the screen here. Oops. Try that out. So it looks like garbage here that's being formed, but in the last instance, every little thing gets fixed up. Or it should, because the screen size is less than 512. So we've got stuff from the bottom that's, I guess it works better at the original size. That's probably why it was written that way.
I think you wrote about this in one of the articles in the Smalltalk 80.
Yeah,
Byte.
So with Smalltalk 80, yeah, in the Byte magazine, I've got a whole article on BitBLT, and it shows this as one of the examples. And I think I violated some copyright by rotating a picture of Mickey Mouse.
Oh, right.
Okay.
So next is the Bitmap Graphics.
Yeah, okay. So, yeah, let's take a look at that. So in addition to windows on the screen, we have these little things which we thought about as doors, but at this point in the evolution of Smalltalk 76, we came to want to have separate worlds for working on different projects. And so what this does, when I enter this thing that says demos, it gives me a new copy of the screen, a new copy of the scheduler with different windows on it. And so we can just go in there to do that. What's nice about it, in addition to a fresh screen to work with, it also, Smalltalk 76 recorded all the changes you did. And there was a change set associated with each of these worlds. We called them projects. So that if you worked on one project, you could say to write out the changes for just that work. So it was really like having separate worlds to work with. So, new from user edit. I think what we want to do here is user schedule, default bit rect editor.
You want to use the default size?
Yeah. What I want to do is, I want to get the image that we had. Yeah, I think that's this one. So there we go. We had, we got Alan to draw us a picture for Smalltalk 76. And he drew this one. And it's it's the only image that's sort of sitting in the system that it's easy to pick up and work with. But this was something, a drawing program that anticipated Mac Paint by quite a few years. I guess this was done right about 1976. And so here we have a menu of tools that you can use. These are ways of programming the tools. So you can set the color of paint you want, the scale of gridding you want, the combination rule, whether you want to store it or the bits, how big a pen you want to use. And then these are tools down the side that essentially have those features all built into them. So this particular tool is saying, I want a fine width and I want to use it in gray. Let's actually make it be black here. And so that will let you, and we've got on stamps, this is left over from something we did before. So it should be just drawing here. Okay. And it's got gridding turned on. We'll turn that off. Okay. And let's go to a slightly heavier line width. So now it's just letting me scribble on the screen. Okay. And I could come to a different tool like this one. And it's drawing in gray. And let's see. And it's using specifically O-rings, so you'll see that the gray will go underneath that line there, if you can see that. Whereas if we had done it in storing, it would, wait a minute, I don't think storing is here. Then when I paint with it, it'll obliterate everything, including the black lines. We also have the ability to blow things up, and let's see where we got that. This is a sort of a fat bits editor. So if I wanted to edit the finger on the lute there, whoops, let me see. You can see that's a little BitBLT hack being used to blow up that region of the screen. I didn't do a very good job of getting the finger, but you can see that if I wanted to turn the finger all black at the end, I could do that. And it's happening in real time up there in that image. So we certainly, in all the work that we did, we tried to keep things as live as possible. So that's now, we've now changed the image there. Let's see what other features to show. I don't know, are there any other features that you think would be nice to show?
Yesterday you showed the stamps and you showed, I guess, the different grid options, like 45 degrees.
Let's see if we can do, so stamps, let's try this. So that I've just clicked on set. Actually, let me do it here. And so I'm selecting the area around that part of the pin as a thing, which now should load that image into this little thing up here that says stamp. And so now if I go, let's just see what it does. Set that and use. So that's just painting like that, but let's turn the gridding up to 8. So now it's laying down that image. So you could make I'm not going to take the time to do it, make a little picture of a man, and then you put men all over the screen or whatever. Okay. Yeah, I think that
I think that's it.
probably
And
covers
there's no way to reverse or undo any of the changes we've made.
This editor, I don't think really had an undo feature, but I think that you know, it's been long enough ago that I don't recall. So it has actually changed that, but I think that I don't honestly know about that. What we can do is to open another copy. Let me, so supposing I close this and reopen it, we'll see if it changed it. But we had a way of doing, does it say? Yeah, so it has this file out operation, so that would write a copy of it on the disk, which you could then read in to work on later. And this print bits, that would go to one of our printers and print the image. Yeah. And I don't see an undo, so that's, yeah. Okay. Anything else you think we should cover with regards to the images?
I think that's it.
Yeah.
I had a quick question about the image.
Yeah.
Alan Kay's drawing. But just about the symbolism of it, you know, it does look like a kind of a children's illustration, so I get that part. But is there, you know, there's a pen, and then it looks like there's a
pen and a pencil in his quiver.
Okay.
Yeah.
And is there anything else you can tell us about the symbolism of the elf? Was this just part of the...
I think it was just a fanciful thought he had.
Okay.
Yeah.
Maybe the Tolkien craze of the middle 1970s.
Yeah, I think it's probably as related to that as anything else.
Okay.
Yeah.
Thanks.
And music was always a part of our enthusiasm, so I think that this is sort of kind of all the tools of the arts in the hand of the child. It's a good way of thinking about it.
Is there any significance to the mushroom?
I don't know. No idea about that. I think it just sort of created a fanciful scene. we knew we were in a different world from that. Yeah. Okay. Yeah, I wish, it's unfortunate I'm not a better artist to play with this, but people did a bunch of neat pictures. Bob Flegel did especially a bunch when he got playing around with Smalltalk. Okay, so let's get back to, I'm going to close this just to save space. And actually, while we're at it, we can find out if we've got a preserved version of that. And we'll just go to here. Yeah, okay. So it, we have affected the one that's inside the image here. Yeah. Okay, close. And we'll go back up here.
So Dan, was that we were just exiting the demo world or demo project and coming back to
the over project?
Okay.
Yeah. Sorry, I should have explained that. Want me to do that?
Yeah.
So you have essentially these sub views.
Yep. Yeah.
So now we're okay. Yeah. So now we're back.
So you may recall this was a sub-project called Demos that we came into, and all the projects essentially exist in a tree. You could have a bunch of them. And then when you want to go back to the overview, you'd use this command. And it was very simple. It simply swapped the change sets and swapped the schedule, the array of windows on the screen, and then it didn't even bother to repaint them. So you you have to go and enter them to repaint them. But yeah. So one of the things I mentioned was about the having the ability in Squeak to work on the primitive behavior in a high-level, easy-to-debug source language. One of the powers of that was that it was really easy to port. Also, I figured out how to do how we could do blitting and doing rotations and scaling as a part of that same code, which I never would have tackled that if it had to be some sort of C code or something like that. But in Smalltalk, I just played around with it and actually got most of this working when we were at an offsite meeting. We did most of our good work at offsite meetings. Anyway, so in Squeak, we did the implementation of BitBLT for color, and not just for color, but for all the different color depths and all the different byte orderings for all the different machines, so that it would continue to be really compatible from one system to another. And one of my favorite tests of that is this, what we call this, the Squeak Mandala, and that's, let me just execute this here. So what this is showing, basically it's when I move my mouse from left to right, it's rotating, it does a rotated copy. Let me, if you look this, you'll see that's a copy of the screen rotated, but there's also been a change in the color map. And as I come closer in here, I'm coming closer to scale of 1. And as I move the cursor, as I move the cursor left and right, there's a rotation involved also. So here, if I go to the left, it's a rotation to the left, and here to the rotation to the right. And then as I get closer and closer to the center, you can see it gives you more and more copies because you're closer to a unity scaling. And you can see this is all pretty performant. And we were able to do that because although it was written as general Smalltalk code, we had a translation from Smalltalk to C for the production interpreter. And it's especially fun when you get down to, when you get down near unity scale. You get all of these neat patterns. And when you actually get down to unity scale, you can see it sort of takes a while to settle. And then if you go beyond unity scale, it gets truly crazy. And we also could synthesize music, so we spent a lot of time just enjoying the diagrams and the music. So this is a pretty good test of what you could do with just a single operation like BitBLT.
And you did this when you were at Apple? Or?
It was at Apple Hill, yeah. We had a yearly offsite at Apple Hill where Alan collected people from education and from technology, and we had some great meetings there talking about the wonderful things that you could do with technology and education.
So this is after you left Xerox?
Yes.
Okay.
Yep.
So approximately 80s, or was it later than that?
It began, I think, in the mid-'80s. I'm the wrong person to ask about some dates. Back then.
Right.
Yeah.
But you mentioned the C implementation of Smalltalk, and that was done.
So okay. So that was free. So when we did Squeak, we got it running. We essentially took the old the Apple Smalltalk interpreter and wrote and used it to implement the simulated version of Smalltalk that was in the blue books that were published, and that became a self-supporting system. But the next step in that was that John Maloney wrote we wrote it in a style that did not do actual message sending. It used our syntax, but it was something that could be translated to C. So he wrote this translator to C. We were getting Squeak built all using running it in simulation mode, and it just barely ran fast enough to be productive. But one day we got the C translator working well enough that it produced a file of C that was equivalent to the interpreter that we had been using, that was all debuggable. And at that point, it became a product competitive version of Smalltalk. So we never had to work in C. We could do all of our work in Smalltalk, and it was sort of like there was this button you could push, and out would come a C program that would be a good, efficient interpreter. And that has continued pretty much to this day, and people have done some serious other, especially Elliot Miranda has done some amazingly performant interpreter designs that where all of the work has been in high-level source code. So,
should we move on?
So yeah, let's do that. Fun stuff.
Earlier you mentioned the importance of the integrated development environment and the browser and the debugger. Could you talk a little bit about that?
Yeah, well, so the development work that we did, we just kept doing the next thing that we wanted to do, we had windows working and menus, and it was really it was Larry Tesler's work that he came up, or at least he was the first person in our group who did this notion of windows with separate panes. We had a code development system that was not browser oriented. You would actually see all the code of a given class as a long sort of galley. And he came up with this paned browser notion. And we at that time had the software to support it well. And we, as you saw with the debugger as well, that was a good case where, because you could see both the code for the class and the method you were running and the state of the temporary variables and instance variables all in one compact way. So we used that internally, and we would give demos in the outside world. And I think just about everybody who saw those realized that that's how they wanted to be working as well. And it just, it's a great example of tech transfer from just seeing a demo to knowing that that's the natural way to work.
And could you talk a little bit about the creation of windows themselves, overlapping windows?
So we had windows from pretty much the very first in Smalltalk 72. I guess the very first implementation of, when we first got it running, it was sort of a what you call a REPL window, a window you could type text into and have it executed in a separate display up above. But Alan was working on that, and he worked with Diana Mary to get that bottom REPL window replicated so that you could have several windows on the screen. and then that got picked up, and we just kept doing more and more with that. With the kids, so much we didn't do that because most of what we did with the kids were graphic applications. But Larry certainly picked it up and did a lot with the Gypsy text editor and other text editors. So we were very lucky that several Smalltalk implementations that ran on the Alto have been preserved, although they're not especially easy to work with. They're the ones that I have access to are preserved as essentially what you might call core dumps, memory dumps of just the bits that were in the Alto memory when it got saved. So it's just a bunch of data and Nova instructions. But it occurred to me it ought to be possible to resurrect that if I simply wrote, if I could figure out the format that the Alto stored that, and that was a known format, a so-called SWAT format, where all of memory could be outloaded that way. And I did know that the Alto used the Nova Data General Nova code instruction format. So I looked that up and started pawing around to find out where things were. And I wrote in the Lively kernel, which is a live coding JavaScript development environment. I started to write an interpreter for Nova code. And this is the point that I got to, where this is a disassembly of Nova code instructions in the Alto memory. And down below here are the contents of the accumulators in the simulated Alto, simulated Nova. And so when I say restart, you can see, let's see, where is it? Let's go up just a little bit. Yeah. So the place where it is, when I say restart, the place where it's currently started is right following this location called outload, because that's the last thing that executed that caused the memory to be stored onto disk. Okay, so it makes sense that when it's loaded back in, that's where it'll be. And so here now, you can step through the actual machine instructions that way, and it's doing all the jumps and tallying things with the accumulators, and then you can go into full run mode, and now it just is showing how it's simulating. But I can now go and look at what's happening on the screen by saying show the screen, and then it goes to full speed emulation. Okay, and so now this is that Smalltalk version starting up, and it has printed "Welcome to Smalltalk" of May 30th, whatever year this was. It's probably 1973 or 4, and this is the Alto prompt, meaning it's waiting for you to type something in, and I should be able to type in an expression, 3 + 4, and it prints 7. We always test it also with 355.0 over 113, which prints something very close to pi. And that tested out all the floating point operations. So by this time, almost everything in the interpreter had been tested. So then you could type other things in here, such as for I to 400 do, and Smiley. Smiley was the name of our turtle for the turtle geometry work. Smiley go I and turn, not 90 degrees, but a little bit less, 89. There we go. It's really pretty impressive what JavaScript can do in a browser with a level of emulation to emulate the Nova code to emulate this language.
So this is actually a version of Smalltalk 72 that we're seeing.
Yes.
Yeah.
Yep. And this is one of those images that we can find and work with. Yep.
Are there any animations that we can show in this?
The one that I was trying to pull out is when I first did Smalltalk 76. Alan was disappointed because he felt like it kind of left the kids behind, both because it had a somewhat more complicated syntax, but also because we didn't have the animation system that we had in Smalltalk 72. And I said, that's no problem, you've got BitBLT, we can do animation. And so I had this really simple demo which ran 3 things around the screen. One was a shape, another was a donut, and it used the BitBLT masking shape so that and all of these would then bounce off the screen. So when the donut came in front of the other one, you could see it through the hole, but not there. So that was demonstrating BitBLT being able to do that. And the last thing it had was a little square window. And in that square window was displayed someplace on the screen. So you'd see like a piece of a browser and it's bouncing around here. But you could move that over here, and when you got to where it overlaid itself, when they crossed, you'd see this endless tunnel of repeated graph. So it was a really fun demo, but I could not find that here. And so I just last night got the list of all the file names that are in all the 121 disks, but I haven't had a chance to go through that. And it would, right now we don't have an ability to to get things onto this disk to file in. But if I can recover that and get it to work, we can have a little seance here and we can add that in. But
Is any of the work for, obviously not the music output, but the music composition stuff available to show in this image?
Not really,
Okay.
because that work was done in the earlier Smalltalk, and that was one of the things that sort of got left behind, that we then picked up in spades when we got Squeak running, so that we were actually doing the synthesis, and we had our own like score, MIDI score display and stuff. But no, that was left behind for a while, and part of the reason was that Smalltalk 76 required most of the microcode space that we had available, and the microcode was also being used to do the old animation system and the old music system, so they couldn't coexist, except on the Altos that we didn't then have that had a double size microstore. So, and I've thought of reviving that in one of our emulations so that we could do that, but it's that's how history was, and the newer systems have that built in.
I have maybe one concluding question, and it might be too broad, so if it is, don't answer it. But the question is, it seems like this, idea of an environment and a language that was all message-based, this sort of object-oriented paradigm, also where it affords this kind of continual bootstrapping to evolve new systems, really has captivated you. And I was wondering if you could just, and it seems like it's been sort of an intellectual journey for you for a long time. And I would just be interested to hear for you, if you can talk about like what has seized you about it to be with it for so long and develop it for so long, if you could speak to that.
Yeah. Yep. Well, I think the heart of it is computers are active things, and they're just supremely active. That's what they give you. And it's, I guess, my passion, or the things that I've gotten excited about. I mean, they're other people's passions too, but has been to serve that for other people and for my own creativity by sort of grabbing onto the next thing that feels like leverage. So when I talk about the history of all the Smalltalks from 72 to 74 to 76 to 78 to Squeak, there's a theme there, which is a system that's live and it's giving you leverage, and each time more leverage or more speed or more something like that. And then with each sort of new step forward, there are more things that can be done. So you can, now we can do large systems. Now we can do big address spaces. Now we can do garbage collection. Now we can do color. Now we can do animation. All music simulation. The music simulation in Squeak is really neat. So that's the thread there is of live coding. I mean, the thing that's nice about liveness is that it's just so motivating, and I think, when I look back on our time at Xerox PARC, and I've mentioned this, the system we worked with, at least early on, ran 10 times slower than what the guys in the computer science lab were doing. But the turnaround time for change for us was typically a second or two after we hit the command character. So we were on it. And that's the fun thing is, when you know what you want to do, it's just, you get there as fast as you can, and the thing you're building is helping you do that. That's I like that, and it's not, so I've been talking about it in terms of the sequence of Smalltalks, but it isn't just Smalltalk. Sort of any tool you get. I mean, I've had so much fun with other systems, just doing what they can do. I mean, I remember having a lot of fun. I got one of these first tiny machines that could run VisiCalc, or actually I think it ran something a little bit more powerful than that. And I spent a cross-country plane trip doing Pig Latin in it because you could, and it was live. I could, each thing I tried out it could do. So it isn't just Smalltalk. It's sort of any kind of live system that gives you leverage. I loved APL that way, and you can see the fact that we've sort of kept infix arithmetic in Smalltalk is because of APL, and Smalltalk is a nice actually system for modeling APL because it's got the sort of the polymorphism of the different layers of arrays, and it's a fun program to write in Smalltalk.
So is it almost in kind of a form of this liveliness is kind of like an interactivity with the system itself, if you will. It's more than like interacting with a program or an app.
Yep.
It's with the entire environment on the computer, if you will.
It's feeling the strength of this new thing. And I think there are musicians that are like that. You hand a musician a new instrument, and things right away they'll be doing things. Chris Jeffers was that way with the Alto. When we first got the music running on the Alto, we didn't yet have the organ keyboard hooked up. We hooked it up to the Alto keyboard, and which allows multiple key presses. And he actually, he sort of like was this for a couple of minutes, and then things started coming out, and before he was playing it. So I think that's I don't know if it's what you say what an artist does, but creative people, when they get a hold of some clay and they start making it into something.
Thank you.
Yeah. It's a nice question.
Yeah. I think you talk about this in one of your Byte articles, actually, in the magazine over there on the table. You talk about sort of the instant response and the kind of creativity that liveness allows, and that was sort of like becomes a philosophy in a way.
Yeah, yeah, and I think and in terms of serving users, that's what users want. There's both the immediacy, and then you want it to be in their terms as much as possible. And that's what some of these advances in the interface have afforded us.
Right. And it definitely makes software development more productive.
Sure. Yep. Yep.
Not having to wait a day for your card punch, your printouts to turn around.
Yeah, and it's a compounding of productivity, because on the one hand you're getting it done sooner, but on the other hand, it's motivating, so you keep going forward. Yeah. And there I find comprect here. And here it says, reverse this area, the R, from black to white. And let's do, so something we could do is to actually put another method here. So right now what it does is it simply complements the rectangle. But we could also complement a rectangle. Let's do this. We could write R translate by 1 at 1. Let's see. I think what we've got to do. What I want to do is I want to make a copy of this rectangle R that's offset. And if I do that as well as complementing the regular rectangle, then it should make an outline around the selection. Okay, so let's try compiling this. All right. Let's see where we are. So this is the point at which we stop. You know what I need to... guys, we may be hosed.
Oh, did we delete something?
No, but I think we just quit with an error in the system. I mean, we got a... let me see. Let me just give some thought to this. It's the wrong character here. And
oh, did you type the...
I typed an @ sign instead of the make a point.
Oh, right.
So, and
you need to type Control-O.
Yes, but the only thing is that we did this in the very heart of the system.
Ah.
And There may not be a way out of here. I'm going to quit.
There's no way to revert the change now that it's compiled?
No, that's, yeah, that's right. There's not. We could start from another copy of this if we had another copy.
Yeah, well, do you want, is there anything to try now, or are you pretty sure that we need to do that, Dan?
Pretty sure we need to do that.
Okay.
I'm going to try quitting and resuming, but I'm pretty sure if you're really fast, you can stop it before it does this, but it wrote a checkpoint, I believe.
And I guess we'll know for next time, have 2 disk packs.
Yeah.
Yeah, right. Yep, it's faithfully preserved.
Everything, yes. Is the downside of making live changes.
Yep.
Which
yep.
is actually kind of a great demonstration
Yeah.
in its way.